In this example, I want to demonstrate the previous theorem, right? I mean, we've already proven the theorem, so it's not that we necessarily need it, but let's look at some concrete matrices. Well, I should say a concrete symmetric matrix to kind of show you exactly what the previous theorem was telling us about the orthogonality of eigenvectors for a symmetric matrix. So you can see this 3 by 3 matrix up here. A, which is symmetric, of course. You'll see that as you swap positions on the diagonal, you get the exact same matrix again. And it can be shown that the eigenvalues of this matrix A are 8, 6, and 3. There's a calculation involved there. You'd have to compute the characteristic polynomial and factor it and such, but that can be done. And you can also check that with each of these eigenvalues, you can find their corresponding eigenvectors will be -1, 1, 0, -1, -1, 2, and 1, 1, 1. So again, we're not going to go through the details of this, but one could go through the whole enchilada and find these eigenvectors and eigenvalues. What I want to proceed to do is show you that these eigenvectors are in fact orthogonal with each other. So if we take the first eigenvector v1 and dot it with v2 right here, the dot product would give us a 1 minus 1 plus 0, which is equal to 0. So we see that v1 is orthogonal to v2, as to be expected. Next, we take v1 dot v2. In that situation, you'll end up with -1 plus 1 plus 0. So that's, again, also 0. And thus showing us that v1, oh, I said v2 there, I meant v3, sorry. v1 dot v3, that's equal to 0. So we get that v1 is orthogonal to v3, like so. And then finally, if we take v2 dot v3, make sure you get it right this time, dude. You'll end up with -1 minus 1 plus 2, that's equal to 0, thus showing us that v2 is orthogonal to v3. All right, so we can see that these eigenvectors are in fact orthogonal with each other, and you can verify that these are in fact orthogonal, or these vectors are in fact eigenvectors for this matrix. For example, if you take A times the vector 1, 1, 1, you can see very quickly that for the first entry, you get 6 minus 2 minus 1. You're going to get -2 plus 6 minus 1. And then finally, you get -1 minus 1 plus 5. And in all instances, those add up to be 3. Right? These are in fact the real McCoy here, all of the eigenvectors and such. But what I want to do is carry this problem just a little bit further, sort of showcasing what's going to be coming up in just a second. Because we have these eigenvectors and eigenvalues, we can actually very quickly construct construct a diagonalization for the matrix A here, right? So we've seen in the previously that a diagonalization can happen when we find a non-singular matrix P, a diagonal matrix D, and the inverse of P, like this. It's a factorization where D is a diagonal matrix, and in this diagonalization, we're going to get these 3 by 3 matrices, like so. And the diagonal matrix is just going to coincide with the eigenvalues of the matrix here. So we have 8, so we get 8 in the diagonal. We're going to get 6 as our second one, so we get 6 in the diagonal there. And then our last one is a 3, so we're going to get a 3 right here. We'll get zeros everywhere else because it is a diagonal matrix after all. Then we will put in the eigenvectors right here. We put those into the matrix P, but before we do that, we do want this. I mean, we can get away with like this -1, 1, 0. That's perfectly fine. We can stick then the second one in right here. Put it in there. In which case, then we get -1, -1, and 2. And then finally, if we stick in the third matrix right here, that would go into the third column. We get 1, 1, 1. So we can construct our matrix P by using the eigenbasis that's in front of us. And then we'll compute P inverse right over here. But I want to make one slight modification to this. A modification that will make much more sense in just a second. So because after all, when it comes to the matrix P, I just need to have an eigenbasis. It doesn't have to be the exact 3 I have in front of us. What we can do is I'm going to make the substitution that instead of using v1, I'm going to use the vector u1 which is equal to 1 over the square root of 2 times negative 1, 1, 0, like this. So we get negative 1 over root 2, we get 1 over root 2, and we get 0. Basically, I just took the normalization of our vector there. The normalization. I computed its length and divided it out. And similarly, I'm going to do this for u2, which notice that the length of this vector is going to be the square root of 6. So you get 1 over the square root of 6 times negative 1, 2. And so let's see. I don't know if I can squeeze that all in there, so let me give myself a little bit more space. So remember, u1 was negative 1 over the square root of 2. We get 1 over the square root of 2, and then 0. So for u2, we're going to get negative 1 over the square root of 6. We're going to get, again, another negative 1 over the square root of 6, and we get 2 over the square root of 6. And then lastly, for u3, I want you to notice that the length of v3 is equal to the square root of 3. And so the vector we're going to squeeze in here is 1 over the square root of 3, 1 over the square root of 3, and 1 over the square root of 3. So why did I go about orthogonal or normalizing these three vectors right here to put inside of P? Well, the issue is that since these vectors v1, v2, v3 are already orthogonal to each other, if I normalize, that makes this eigenbasis an orthonormal basis. And if you have a matrix whose columns form an orthonormal basis, that's what we called before an orthogonal matrix. Making connections with what we saw before. And orthogonal matrices have the property that their inverse is none other than just its transpose. So P inverse is just P transpose. And so I don't have to go through this inversion algorithm to calculate P inverse. I can just take the transpose of this thing if it's an orthogonal matrix. So taking the transpose, you get negative 1 over the square root of 2, 1 over the square root of 2, and we're just going to clear this out for a second. And then we get a 0 right here. That's our first. So our first column becomes our first row. Then we get negative 1 over the square root of 6, negative 1 over the square root of 6, and 2 over the square root of 6. And then lastly, we end up with 1 over the square root of 3, and this happens 3 times. And so we can very easily calculate the inverse by taking the transpose instead of the usual inversion algorithm. So there's sort of a simplicity. That is, I could just normalize the vectors in this eigenbasis, which is fairly easy in terms of computation, right? And then if I'm willing to normalize them, then I essentially have to put no effort into finding the transpose. So there's a little bit of a trade-off there. And so we get this diagonalization, a diagonalization that uses an orthogonal matrix right here. And so this right here is actually the idea we're leading up to, and we'll see this in the next video in just a second. Click it so you can watch it.